organic compounds. So we're just going to learn a little bit about organic compounds. Early chemists divided matter into two different types of compounds, organic and inorganic. In everyday life in American culture, the word organic makes me think of pesticide-free produce, right, and vegetables and things. And organic is safe, organic is good, okay? In chemistry, organic is not safe. Or a lot of organic things are extremely toxic. The word organic just means it comes from living organisms, okay? Organic means it comes from living organisms. Things that did not come from living organisms were called inorganic. Turns out that organic compounds are a lot easier to decompose. A lot of them burn. But they're very difficult, or they were very difficult to synthesize, whereas the inorganic compounds were much easier for early scientists to synthesize in the lab. So today we make a lot of organic compounds in the lab. Organic compounds are everywhere. Your body is full of them. We define an organic compound in chemistry as something that's mainly composed of carbon and hydrogen. So organic compounds are primarily carbon and hydrogen. There can be other elements in there. Common ones are oxygen, nitrogen, phosphorus, sulfur, but there could be others. The key element is carbon. So here's the smallest organic molecule, methane. It's just a carbon and 4 hydrogens. Carbon is a unique element. It frequently bonds to itself, and it forms covalent bonds with other carbon atoms, and it can form long chains, and those chains can branch. You can make ring structures. It's like the ultimate building block. It can do all kinds of things. It can form single bonds, double bonds, triple bonds with other carbon atoms or with other elements. So it's really a pretty awesome element. So here's some examples of some organic compounds. Here we have propane. We've got 3 carbons bonded together, and then the hydrogens are filling in around. Carbon always wants to have 4 bonds. It could be 4 single bonds. It could be 2 double bonds. It could be 2 single bonds and a double bond, whatever adds up to 4. So here we've got each carbon with a double bond and 2 single bonds. Here's a triple bond between the 2 carbons. Here's carbon double bonded to oxygen, and it's bonded to oxygen over here, and here it's bonded to another carbon. All of these are organic compounds. This one we have a ring around the rosy with carbon atoms. We call that a ring structure. So the second year majors courses in chemistry is organic chemistry, and that's where you study these sorts of molecules. So hydrocarbons just have carbon and hydrogen, hydrocarbon, hydrogen, carbon, and then there are functionalized hydrocarbons, which have some extra details on them. So we can take all compounds, divide them into inorganic, and those are the sorts of the ionic compounds and the acids and the molecular compounds that we learned how to name, and organic compounds, and these can be divided into hydrocarbons or functionalized hydrocarbons. Hydrocarbons are commonly used as fuels. So oil, gasoline, liquid propane, natural gas, those are all hydrocarbons. They burn and give off a lot of energy, and the products of their combustion are actually quite clean. The pollution that we get from gasoline, burning gasoline, is not from the hydrocarbons, it's from the other stuff that happens to be in the gasoline. So I'm going to teach you how to name basic hydrocarbons. So there are 3 groups. There are hydrocarbons with single bonds, and those as a group are called alkanes. So the suffix here is important. Alkanes, that means single bonds only. Alkenes have at least 1 double bond. Alkynes have a triple bond. So we're just changing the vowel there, A, E, and Y, 1, 2, and 3. So the naming pattern here is we have a base name, and that name will be determined by the number of carbon atoms. And then the suffix is determined by whether there are multiple bonds and what kind they are. So the suffix could be ein, een, or ein. Base name comes from the number of hydrogens. So let's skip to number 5, pent. That's like the prefix penta that we used in other nomenclature. Hexa, hepta, octa, nona, deca. Those are all the same, right? Just without the A's. The first 4, I don't know why. It just is, and we have to deal with it. So for 1, the prefix is meth. For 2, it's eth. 3 is prop. 4 is bute. How do you remember that? Mom eats pickled bananas. Oops. This isn't in your book. This is just what I learned in college. Mom eats pickled bananas. So it kind of makes you think Mom might be pregnant. But methyl, meth, eth, prop, bute. 1, 2, 3, 4. If you've got a better way, go for it. Then the suffix ein, een, or ein. So we can take any of these prefixes and combine with one of these suffixes. So you could have methane, you could have butane, you could have nonene, or nonane, or nonine. Spelling here matters. So here we have methane. Meth is the prefix that means one carbon. So there's 1 carbon. The hydrogens, there's just enough hydrogens on there so that all the carbons have 4 bonds. Here's propane. Prop means 3. So we have 3 carbons and enough hydrogens around it to make 4 bonds for every carbon. Here's butane. Bute means 4, so this is C4, 4 carbons. Now it is possible to arrange 4 carbons in other ways. And so this is N-butane. The N meaning this is just a straight chain. We're not going to mess around with anything that's branched. We're just going to learn how to name straight chain hydrocarbons. Here's N-pentane, 5 carbons. And then just draw the hydrogens around. So this is ethene. Eth meaning 2, and the suffix ene says there's a double bond. Well, there's my 2 carbons. The double bond has to be between them. There are fewer hydrogens here because of the double bond. And this one is ethine. 2 carbons, it's a triple bond. And this tells you what these different things are used for. Won't test you on that. What about the functionalized hydrocarbons? So a functional group adds a different function to the compound. You could even argue that a double bond or a triple bond is a functional group because it changes the chemical properties of the substance. If we look at a group of organic compounds that have the same functional group, those are called a family. So methanol and isopropanol are both members of the alcohol family. They're both alcohols. These are their formulas, C3OH, and this one's kind of messy, it's branched. They both have this OH group. That's the functional group that makes it an alcohol. Ethanol is another one. Guess how many carbons ethanol has? 2. See, this is methanol, 1 carbon. Ethanol has 2 carbons. So these are families of organic compounds. So I want you to know alcohols and carboxylic acids and amines. So if I asked you a question on an exam, if I showed you a compound like this and asked you what was the functional group or what was the family that this belonged to, it's an amine. We don't need to learn how to name it, we just need to recognize it. It's that nitrogen in there that makes it an amine. Carboxylic acids have a carbon with this OH group like the alcohols. There's the alcohols up there, OH group. Here's an OH group, but then this carbon is also double bonded to an oxygen. These are the ones that are most common, just that you might encounter. So acetic acid, that is an acid that has acetate ion. C2H3O2 is acetate, right? This is an oxy-acid because there's oxygen in it. It's formed from an oxyanion. So a -1 charge means that it has one hydrogen. So that's how we typically write it, HC2H3O2, because this is the ionizable hydrogen, and it's put together like this. You don't need to be able to draw the structure of that, but this is a carboxylic acid. Many of the weak acids are carboxylic acids. Citric acid that makes lemons sour, it's a carboxylic acid. Okay, so what should we be able to do? Oh, let me fix something here. There we go. Okay, draw the structural formula for nonane. Well, what does the prefix non mean? 9. We need 9 carbons. 1, 2, 3, 4, 5. This is the kind of math you get in OChem. 1, 2, 3, 4, 5, 6, 7. A lot of counting. 8, 9. 9 carbons. Then we put hydrogens on this. And this is actually pretty simple. This is all single bonds. And so to have 4, we need 1 up and 1 down and 1 to the right and 1 to the left. So it's just kind of geometric or something. This isn't what the actual structure of it looks like, but this is how we can draw a very convenient formula for it, structural formula. So I've got my 9 carbons. The name nonane told me that, with single bonds. And then I need to fill in with hydrogens. Gets a little tedious, which is why we don't usually draw structural formulas for things that are this large. So many hydrogens. So you should be able to draw any of the alkanes, alkenes, or alkynes. Now, if this was nonene, let's make this nonene. What does changing the A to the E do? We need a double bond. For Chem 1A, drawing this, I don't care where you put the double bond. In OChem, we care a great deal. Here, we don't care. Put the double bond somewhere. So let's make a double bond right there. Now, what's wrong with this carbon and this carbon? They have 5 bonds, right? So what I need to do is I need to erase some hydrogens. So I'm going to take this one off and this one off. I could have taken the other 2 off. Now this carbon has 1, 2, 3, 4 lines, 4 bonds. So that is nonene. Nonine would have a triple bond somewhere. And again, you need to adjust the number of hydrogens. If I showed you this structural formula, you should be able to tell me the basic name. Okay, so either way. And then I fixed this to align with what I told you I wanted you to be able to identify. What family does this belong to? It's a carboxylic acid. Oops, writing with an eraser, that never works. This is a carboxylic acid. So this OH group may make you think of an alcohol, but the double bond with oxygen here makes it a carboxylic acid.